Okay, so reminders for today, homework 6 is due on the 27th, and then we do have spring break coming up on 4/3 through 4/7, so not next week, but the week after. Agenda for this video, we will be going through section 5.2 and 5.3. All right, so 5.2 is talking about power functions and polynomial functions. So one polynomial function that we've already looked at was the quadratic, the x squared type of function, but a power function is any function x where we can have p be the power. It's any real number. It can be to the third power, fourth, fifth, 100th power, and so on. We also have a number k, a constant, or a coefficient being multiplied at the beginning of this function. And depending on the value of k, your function can have certain behavior when we look at the graph of it. So looking at the even and oddness of a function, if you have a function that has an even power, meaning the p is an even number, so squared to the fourth power and so on, then if k is a positive constant, our function looks something like this. So think about x squared, positive x squared. Whereas if k is a negative number, then the graph will open up. Now, the way we want to represent the end behavior, so what happens at the end of the graph, is we say as x approaches negative infinity, so as x is going towards negative infinity, then f of x, your graph, if it's an even power positive constant, f of x also approaches infinity. And if x is approaching positive infinity, then f of x approaches positive infinity as well. So let's look at this one more time. Now, if k is a negative constant, then we are looking at even power, negative constant, as x is approaching negative infinity. So as these values get smaller and smaller on x, the graph is approaching negative infinity. As x is approaching positive infinity, f of x, the graph is approaching negative infinity. So go ahead and pause the video and look at these odd powers and try to make sense of what's going on at the end behavior, see if that's clear. All right, now that you unpaused, so if we have an odd power, so think about x cubed, the parent function that we looked at last time, and k is positive, we have this waterfall kind of behavior going on. As x is going to negative infinity, f of x is also going to negative infinity. As x is going to positive infinity, f of x is going to positive infinity. If k is negative, so if we have maybe like a negative x cubed, then we have a reflection going on. And it is reflected about the y-axis because the negative is on the outside. And we have this happening. So as x is going to negative infinity, f of x goes to positive infinity. As x is going to positive infinity, f of x goes to negative infinity. And this is true for any odd power. So you can have x to the fifth power, x to the seventh, x to 101 power. So let's look at a function that's given to us and try to describe the end behavior of this graph. And we want to describe it using this notation. So notice we have x to the 8th power. So our power is a even number. Note p is 8. Our function is even. And then also k, the constant that's being multiplied in front of x, is a positive 1. So k is positive 1. So then we have even function opening up. Our function, if we were to just do a rough sketch, is going to look something like this, maybe a quadratic kind of feel, not quite a quadratic because we have to the 8th power, but both of those arrows do point up. So let's describe that in terms of using our end behavior with our x and infinity symbols. So as x approaches negative infinity, f of x will approach positive infinity. So let's put all of that into words. As x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, f of x also approaches positive infinity. All right, let's look at another one. What I would suggest you guys do is pause the video, attempt this before looking at the solution, and then we can compare them. All right, so notice here we have an odd powered function, so and k is negative. So note odd power and negative coefficient. So the function will look something like this. I don't care what happens towards the middle. We will look at that later, but for now, we're just interested at the end behavior. So whatever's happening towards the end. So as x is going to negative infinity, f of x goes to positive infinity. And as x goes to positive infinity, f of x goes to negative infinity. All right, so then looking at what a polynomial function is, it's any function. So the ones we looked at right now didn't have any middle terms. For example, it was just x to the 8th, x to the 9th, and so on. But we can have middle terms being added there. So a polynomial function, we let n be some non-negative integer, is a function that can be written in this form. So a chain of power functions added or subtracted together. These AIs, so these are just some coefficients, they can be any numbers. As long as the first one is not 0, because if it is, then this whole thing goes to 0 and we don't have an nth degree polynomial anymore. And each one of these is a term of the polynomial. So this is a term, this is another term, and so on. Now our leading coefficient is, so if you look at your leading term, so the term that has the highest degree, the highest power, the leading coefficient is the number that's being multiplied by it. And the degree is whatever that highest number exponent is. We usually write it from greatest to smallest coefficient, and this is the general form for our polynomial. So let's look at a few polynomials, and we want to identify their degrees, leading term, and leading coefficient. All right, so f of x it actually isn't written in highest to smallest degrees, so let's rewrite it. So this will be negative 4x cubed plus 2x squared plus 3. Here is our leading term. Is negative 4x cubed. Leading coefficient is negative 4. And our degree is the highest power, which is 3. Let me put colons here instead of equal sign. So go ahead and pause and try G of t and P of t, and then we'll compare. All right, G of t, I will write as leading term, leading coefficient, and degree. Okay, so our leading term is 5t to the 5th. Leading coefficient is 5. Degree is also 5. And then for h of p, our leading term is negative p cubed. Leading coefficient is -1, and degree is 3. Okay, sometimes we might be given a graph. So here we want to come up with the end behavior of this, and then try to kind of think about what possible degrees we can have for this polynomial. All right, so end behavior again as x approaches -infinity, our f of x will approach -infinity as well. And as x approaches positive infinity, f of x also approaches positive infinity. Now, this type of behavior, it's an odd function. So the degree of this has to be of some odd number. So we can have an odd degree. We don't know what this odd degree might be yet, but we will later, depending on how many turns a function has, how many x-intercepts, and so on, you can come up with a degree. But for now, all we know is that the leading coefficient must have an odd degree. The degree must be odd, and the leading coefficient must be positive since it has the behavior of a positive k value. So we have degree is odd, leading coefficient is positive. All right, now given polynomials, we can also find their x-intercepts and their y-intercepts based on their function. If the function is factored out for you, great, or work is cut short. If it's not, we do have to factor it first and then be able to determine what these x-intercepts are. So remember, to find the x-intercept, you make y equals 0, and to find the y-intercept, you let x be 0. So let's do the y-intercept first. Let x be 0. Then f of 0, so we're just plugging in 0 for x. 0 minus 2, 0 plus 1, 0 minus 4. So this gives me -2 times +1 times -4, which is +8. Again, don't forget, x and y intercepts are points, so don't leave it as just 8. Write it as a point. So the y-intercept is 0, 8. Now for the x-intercept, this happens when f of x is equal to 0. So x-intercepts happen when your y is 0. So let f of x equal 0. Then we rewrite our function. So this is 0 is x minus 2, x plus 1, x minus 4. All right, now let's apply that zero product rule. I have 3 things multiplying to give me 0. One of them has to be 0. So either x minus 2 is 0, x plus 1 is 0, or x minus 4 is 0. So solving, either x is 2 or x is -1, or x is 4. So then your x-intercepts are, again, your points 2, 0, -1, 0, and 4, 0. There's 3 of them. And if we go up here, if we were to factor this out, your degree will be a degree 3 polynomial. Since x times x times x will give you x cubed. And notice you have 3 x-intercepts. All right, let's try another one. We want to find the x and y-intercept of this function. However, it's not factored, so we do have to factor it first, then look for these x and y-intercepts. So go ahead and pause the video, attempt it, and then unpause and compare your answers. All right, again, notice our degree, if this is a degree 4 polynomial, so it means we have a possibility of 4 x-intercepts. Y-intercept, you can only have 1, because if you have more than 1, then you don't have a function anymore. The graph is touching the y-axis twice, and it will not pass the vertical line test. So let's do our y-intercept first, because that one's kind of the easy one. So y-intercept, let x be 0. So then f of 0 is 0 to the 4th minus 4 times 0 squared minus 45. Well, these go away, so it's just -45. So x-intercept is then 0, -45. I'm sorry, y-intercept, not x-intercept. Y-intercept, there we go. Now x-intercept. This is when the whole thing is 0. Meaning 0 has to be x to the 4th minus 4x squared minus 45. Okay, again, I have no idea what values make that 0 because it's not factored. So let's factor it. Now looking at this, I don't know how to factor a degree 4 polynomial. So we kind of have to think of a way to factor this using something we know how to do. So notice this kind of looks like a quadratic, with the exception that this is x squared squared. So let's do something called a substitution of variables, and that will maybe fix our problems. So you want to pick some variable and let x squared be that variable. So we're gonna let, I like to pick u be x squared. Then we have 0 equals x to the 4th is now x squared squared minus 4 times x squared minus 45. But I can substitute in the u being x squared. So this is really u squared minus 4, x squared is u minus 45. Okay. This is a quadratic. I know how to factor that. So you can either use the quadratic formula, completing the square, or you can just factor it, because this does factor. And this ends up being u minus 9 times u plus 5. But now we have to substitute back in, because I don't want u, I'm solving for x. So remember, u is x squared. So 0 is x squared minus 9 times x squared plus 5. I have a difference of squares here. So we have 0 is x minus 3, x plus 3, x squared plus 5. All right, now we have 3 things multiplying to give me 0. Let's solve for them. So this tells me x can be positive 3, or x can be negative 3, or x squared can equal -5. Well, if I were to take the square root of -5, I'll end up getting an imaginary solution. So there's no real solutions here. I can't put that on a graph for an x-intercept. So no real solutions here. So then my x-intercepts are plus and minus 3. So x-intercepts are 3, 0 and negative 3, 0. So notice, again, it's a degree 4 polynomial. Your maximum amount of x-intercepts you can have are 4. We have 2 real ones, and then you would get 2 imaginary ones from there. But we don't care about finding the imaginary ones, but there are 4 counting imaginary and counting a repeat. All right, something fun to note. So we did talk about a polynomial of degree n has at most n x-intercepts. And it will also have n minus 1 turning points. A turning point is when you are following your graph and then you turn to change the direction. So instead of increasing, now we're decreasing. And then we turn, increase again. And then these are your x-intercepts. And then here's our y-intercept. So we have 1 turning point, 2 turning points here, 3 x-intercepts. This is probably a degree 3 polynomial, just looking at the graph. So now let's just look at this and try to come up with the behavior of the graph. Find the maximum number of x-intercepts, turning points. We don't need to find the actual x-intercepts, just how many there would be. And just talk about what it would look like just by looking at the graph. So go ahead and pause this and think about how many turning points we might have and what the degree is, and then unpause it and compare. All right, notice, so this is a degree 10. So your x-intercepts, at most, there's 10 of them. And then our turning points, so there's n minus 1, 10 minus 1, there's at most 9 of them. All right, and that is the end of 5.2. Then moving on to 5.3, we'll look at the graphs of these polynomials a little more. All right, so now if you factor out a polynomial and you end up getting some x minus h. So inside the factored form, maybe, I don't know, maybe it's x minus 3. Some number, h is some number. But if we have a repeat of that, so what if it's x minus 3, but then there is a squared term at the top? Then that squared term tells you that the x-intercept at 3 will have a multiplicity of 2. So there, it happens twice. If you have even multiplicities, then at that x-intercept, your graph will bounce off on there. If you have an odd multiplicity, it will cross that x-intercept, and we'll look at what that means on the graph. Now, if f is a polynomial function, then we have something called the intermediate value theorem, which is something you will look at in calculus in more depth. But it says that if f of a and f of b have opposite signs, so if one of them is a negative number and one of them is a positive number, then there has to be some value in between those where your f of whatever that value is will give you 0. So it will cross 0 at some point. So let's look at what that means. So if you have some f of a, which is a negative value, and then you have f of b, it's a positive value, well, doesn't that have to cross 0 at some point. So that's just basically telling you if your graph changes signs, then in between that sign change, there has to be a value where you will get an x-intercept. Well, it will cross that graph. So let's look at this graph right here, or let's look at this function right here. It's a polynomial function, and let's graph it. All right, so things that I am interested in looking at. This is a degree 6 polynomial, so I should be expecting at most 6 x-intercepts. Note, we have at most. And again, we want to graph this without a graphing calculator. We want to graph this with all the things we know. Okay, I can find the x-intercepts. I can find the y-intercepts. I know there are 5 turning points since it's a degree 6. We have 5 turning points. Turning points. I know it's even, so the end behavior of the graph is going to do something like this, or it might do something like this, but since my leading coefficient is a positive one, this is what it's going to look like. So the end behavior as x goes to negative infinity, f of x will go to positive infinity. As x goes to positive infinity, f of x will also go to positive infinity. So we have positive infinity at both ends. What else? I can find x and y-intercepts. Let's do that. So y-intercept when x equals 0. So then f of 0 is 0 to the 6th minus 3 times 0 to the 4th plus 2 times 0 squared. And that's just 0. So x and y-intercept for that case. So y-intercept is at 0, 0. Let's find the x-intercepts. X-intercepts happen when y equals 0. So then we have 0 equals, what is it? X to the 6th minus 3x to the 4th plus 2x squared. Let me double check it. Yep. So let's factor. I can take out an x squared from everything. Now we have x to the 4th minus 3x squared plus 2. Let's do some factoring there. I think we could do that. So let's factor x to the 4th minus 3x squared plus 2. We're going to let u be x squared. Then we have x squared minus 3x squared plus 2, which gives us u squared minus 3u plus 2. And this factors to u minus 1 and u minus 2. So these two multiply to give me positive 2, add to give me that negative 3. We're good. But we said x squared was u. So x squared minus 1, x squared minus 2. Okay, so then this whole thing factors to x squared minus 1, x squared minus 2. Then our f of x, so going back when blue, so 0 equals x squared times this stuff, which is factored as this. So x squared times x squared minus 1, x squared minus 2. All right. Let's use our zero product rule. Either this is 0, this is 0, or this is 0. So x squared is 0, or x squared minus 1 is 0, or this is a difference of squares. We could have squared it, or we can just move the 1 over and take the square root as well. X squared minus 2. So here x is 0, or x squared is 1, which tells me x is plus or minus 1 if we take the square root, or x squared is 2, which gives us x is plus or minus root 2. So there is my x-intercepts. So then x-intercepts, we have 0, 0. This happens twice. So multiplicity here is 2. So this is a bounce because we have an even number for the multiplicity. We have 1 at positive 1, 0, multiplicity is 1. We have 1 at negative 1, 0. We have 1 at negative square root 2, 0. And we have 1 at positive square root 2, 0. So all these have multiplicity 1s. And these are crosses. So they cross the x-intercept. All right, now that is enough information for me to sketch a graph of this function. So let's put everything onto a graph. All right, I know my end behavior is going to do something like this. Let's put our x and y intercepts on here. So we have 0, 0, which has a bounce to it. We have negative 1, 0, so this is 0, 0. We have a negative, and these are not to scale at all. I'm just doing a rough sketch. Let's say this is 1, 0. Actually, let me make this a little bit closer since this is root 2, 0. There we go. We'll move it just a little bit closer. There we go. So that it's more to scale, I guess. Okay, so now I want to graph this without moving my pencil off the screen. So I am going to start in this direction, go down, I cross this x-intercept. I have to do some change because I have to cross this other x-intercept as well. And then we somewhere change directions, bounce off of this, change direction again, cross, cross, finish up on this end. That's what the graph looks like, a rough sketch of it. I don't know where these direction changes happen, and I'm not interested in it for now. I'm just sketching the graph. Later on, we can figure out where these happen, but for now, we're just interested in a rough sketch of what does this graph look like. And this is a good enough rough sketch for us. So let's just verify. There are 1, 2, 3, 4, 5, 6 x-intercepts. Notice I counted 0, 0 twice because it does happen twice. And then our direction changes. There is 1 direction change, 2, 3, 4, and 5. And that's what we said it was going to have at the beginning. All right. My suggestion would be to rewind this portion and watch it one more time just to get a good hang of it. And then what you will turn in on Monday on a separate sheet of paper. So this is our assignment. You are going to consider this polynomial f of x, find its end behavior, find the x-intercepts, their multiplicities, the y-intercept, and use everything you know to sketch a graph of it. My suggestion is try it. Do your best, find all the x-intercepts, y-intercepts, and all of that, and then sketch the graph. And you may after you do all of this, you may use a graphing calculator or a computer software to double check your work and see if your graph matches the one that the computer generates. If not, see what happened, go back and try to fix your errors. So don't forget, this is something you will be turning in on Monday in class. All right, so that is the end of this lecture. I will see you guys on Monday.